In this section, we discuss the change of a basis problem. That is, given two bases b1 and b2 of a vector space V, how the coordinate vectors of an element relative to b1 and b2 are related to each other. That is a question. So we begin with a definition. Let S is equal to v1, v2, etc. vn be a basis for a finite dimensional vector space V. Then for any element V in V, there exists a unique set of elements, say C1, C2, etc. Cn in R, so that we have an n-tuple C1, C2, etc. Cn in Rn, such that V is a unique linear combination of these elements C1, V1 plus C2, V2 plus etc. plus Cn, Vn. That is V equal to summation I from 1 to n Ci Vi. Also, on the other hand, given C1, C2, etc. Cn in Rn, there exists unique V in the vector space V, such that V is the linear combination of Ci Vi's. That is sigma I from 1 to n Ci Vi equal to V. Therefore, we can define a mapping which takes each V in the vector space to the coordinate vectors, the coordinate vector of V relative to S. And this mapping is a 1-1 mapping between the general vector space V and the Euclidean vector space Rn. So the mapping which takes V to its coordinate vector relative to S is a 1-1 mapping from V to Rn. This mapping is known as the coordinate map relative to S from V to Rn. So the coordinate map relative to S from a vector space V to Rn is that particular 1-1 mapping, okay, which takes V to the matrix of V relative to S. So here is a notation. Two things to be noted. This particular symbol means there exists a unique. Okay, you can observe that there exists a unique, and also we assume that the basis is ordered. Okay, so for convenience, the coordinate vector of V relative to S in the matrix is expressed in the matrix form. The matrix of V relative to S is the column vector C1, C2, etc. Cn. So the change of basis. This problem is, let B1, B2 be two bases for a given vector space V, and suppose V is an element of V. So in this section, we see how the coordinate vector of V relative to B1 and the coordinate vector of V relative to B2 are related. So we proceed like this. Let B1 be the basis U1, U2, and B2 be the basis V1, V2. So we assume that V is a vector space of dimension 2 for easiness. So that I did not mention in this PDF, but and we can generalize it. Suppose then U1 being an element of V, it can be expressed as a linear combination of V1, V2. So suppose U1 equal to A1, V1 plus A2, V2, and U2 equal to B1, V1 plus B2, V2. Then the matrix of U1 relative to B2 is the column matrix A1, A2, and that of U2 is B1, B2. So consider an element V in capital V. And suppose the matrix of V relative to B1 is K1, K2. Then we change the matrix to B2 relative to B2. Then V is a linear combination relative to U1, B1 as V is equal to K1 U1 plus K2 U2. So replacing U1 and U2 in terms of V1, V2, we get the matrix of V relative to B2 as K1 A1 plus K2 B1. Then second row K1 A2 plus K2 B2. So in matrix form, this can be expressed as A1 B1 A2 B2, the 2 by 2 matrix, into the matrix of V relative to B1. Thus, if P is equal to A1 B1 A2 B2 2 by 2 matrix, then the matrix of V relative to B2 equal to P into matrix of V relative to B1, where the columns of P, say P1 and P2, are given by P1 equal to the coordinate matrix of U1 relative to B2, and P2 is the coordinate matrix of U2 relative to B2. And now let us generalize this to an n-dimensional vector space. Let B1, B2, etc. Bn. Let B1 and B2, where B1 equal to U1, etc. Un, and B2 equal to V1, etc. Bn, be two bases for a vector space V. And suppose V is a general element of the vector space V. Then the matrix of V relative to B1 and the matrix of V relative to B2 are related by the equation the matrix of V relative to B2 equal to P into the matrix of V relative to B1, where the columns Pi for I equal to 1 to n of P are given by the Pi equal to the column vector Ui relative to B2. So what we will do is, in order to change the basis from B1 to B2, we make the matrix P, where P is the column vector which is we express this u1, u2, etc. un of b1 in terms of the elements of b2, and we consider the corresponding column vector. Then P is called the transition matrix. So sorry, I have written translation. It is the transition matrix. Sometimes it is known as the translation matrix also. So it is a translation matrix from B1 to B2, denoted by P as a subscript. We write B1 arrow mark B2. So it means that it is a transition matrix from B1 to B2. Thus P B1 to B2, that is the transition matrix P from B1 to B2 is that particular n by n matrix, where the columns u1, the first column is the matrix of u1 relative to b2, second column is the matrix of u2 relative to b2, etc. The nth column is the matrix of un relative to b2. So similarly, the transition matrix from b2 to b1 is given by the n by n matrix whose first column is the matrix of v1 relative to b1, second column is the matrix of v2 relative to b1, etc. The nth column is the matrix of vn relative to b1. Thus we have the matrix of b1, the matrix of v relative to b1 is equal to the transition matrix from b2 to b1 into matrix of v relative to b2. So the transition matrix will be from B2 to B1, because we are changing the basis from B2 to the new basis B1. And to change the basis from B1 to B2, then the matrix of V relative to B2 equal to the transition matrix from changing to B2. So B1 to B2 into the matrix of V relative to B1. Okay. The columns, there is a remark, the columns of the transition matrix from an old basis to a new basis are the coordinate vectors of the old basis relative to the new basis. So we have certain examples. As a first example, we have two bases, B equal to V1, V2, V3 and B1 equal to U1, U2, U3 of R3, where V1 equal to 2, 1, 1, V2 equal to 2, minus 1, 1, V3 equal to 1, 2, 1. And u1 equal to 3, 1, minus 5, u2 equal to 1, 1, minus 3 and u3 equal to minus 1, 0, 2. Find the transition matrix from B to B1 and from B1 to B. Also, if W equal to minus 5, 8, minus 5 is an element of R3, then compute its matrix relative to B. And using this and the transition matrix, find the matrix of W relative to B1. So you do not calculate the other way. This matrix can also be calculated by expressing the elements of W as the elements as a linear combination of the elements of B1. So, but that is not the way. We have to use the matrix of W relative to B and the transition matrix to compute matrix of W relative to B1. So as the solution, first we will evaluate the transition from B to B1. So what we do is we express the B to B1. So the elements of B are expressed in terms of the elements of B1. So V1 equal to, let us assume A1 U1 plus A2 U2 plus A3 U3. So you will get 2 1 1 equal to A1 into 3 1 minus 5 plus A2 into 1 1 minus 3 plus A3 into minus 1 0. So that gives a system of linear equations. Okay. Sorry, there this particular slide is repeated, so just take care of that. So we have a system of linear equations, 3a1 plus a2 minus a3 equal to 2, a1 plus a2 equal to 1 and minus 5a1 minus 3a2 plus 2a3 equal to 1. Solving this, we get a1 equal to 3, a2 equal to minus 2 and a3 equal to 5. So the matrix of v1 relative to b1 is 3, minus 2, 5. And observe that this gives the first column of the transition matrix from b to b1. Similarly, you express v2 as b1 u1 plus b2 u2 plus b3 v3, and solving as in the above section, we get b1 the matrix as 2 minus 3 1, and similarly v3 on expression we will get the matrix of v3 relative to b1 as 5 by 2 minus 1 by 2 6. Thus the transition matrix from b to b1 is that matrix 3 by 3 matrix whose rows are given by 3 2 5 by 2 minus 2 minus 3 minus 1 by 2 5 1 6. So observe that the first column is the matrix of b1 relative to v1 relative to b1, that is 3 minus 2 5. Second column is 2 minus 3 1, which is the matrix of v2 relative to b1, and the third column is the matrix of v3 relative to b1. Similarly, we can compute the matrix, the transition matrix from b1 to b, and it is given here. As for the third section, let us assume the matrix of w relative to b is k1, k2, k3. So we have again a system of 3 linear equations in 3 unknowns. Solving it, we will get the matrix of w relative to b as 9 minus 9 minus 5. Therefore, we have matrix of w relative to b1 is equal to the transition matrix from b to b1 into matrix of w relative to b. Okay, so which is already computed. b to b1 is 3 2 5 by 2 etc. That particular matrix into 9 minus 9 minus 5. So we will get minus 7 by 2, 23 by 2 and 6. That particular column matrix is the corresponding matrix. So in the same fashion, I have considered another example where the space is P1, the set of all polynomials of degree less than or equal to 1. So it is of 2-dimensional space, and suppose the bases B1 and B2, B and B1 are given by P1, P2 and Q1, Q2, where P1 equal to 6 plus 3x, P2 equal to 10 plus 2x, and Q1 equal to 2, Q3 equal to 3 plus 2x. So compute the transition matrix from B to B1, B1 to B, and also given a particular element, find out its matrix relative to B, and using this find the matrix relative to B1. So this can also be solved as in the previous problem. Okay,